All right, good morning, mathematicians. Here we are at the very end. In this video, I'm going to be walking you through Unit 8, What Do You Expect study guide. This is found on pages 92 and 93 in your workbooks. Okay, so with that, let's dive right in. Okay, so let's read this information here. So the name game costs 20 cents to play. Before the game, there are 30 slips of paper, each with a different student name from the whole class. Okay, and those are put into a bag. A player draws one slip from the bag. If the player draws any name from their table group, in parentheses it says each table group gets 4 slips. Okay, that's important. They win $1. Well, they win $1. So what is the theoretical probability of winning the game? Well, how many total slips of paper do we have? Well, we have 30, so 30 is going to be my denominator, and each group has 4 slips. So it looks like that my probability of winning the game is going to be 4 out of 30. Okay, we're going to keep it at 30, okay? Then we need to figure out what is the theoretical probability of losing this game. Well, that's going to be, if I do 30 over 30 minus 4 over 30, I'm left with a probability of 26 out of 30, okay? So it looks like we're going to lose a lot here, okay? If a team plays the name game 30 times, how much money would you expect them to win or lose? Okay, so we're going to say that we played this 30 times. We know, so let's see, so 30 times we're going to play, okay? And it costs 20 cents to play this game. So every time we play, it's going to cost 20 cents. So we're going to multiply those two things. Okay. So let's do that. 30 times 0.2. Well, that's going to be 60. So that's going to be $6, right? $6 to play. Then after that, so that's the cost to play. Then we need to figure out how much money we're going to win, right? So we win $1 for every win. So we have 4 out of 30 wins. So 4 wins equals $4. Boom. So at the very end, we paid $6 and we win $4. So I'm going to subtract these two to figure out the difference here. 6 minus 4. So it looks like we are in a deficit of $2. So we are going to lose $2 if we play this game 30 times. So is it a fair game? Most likely not. If you're losing money, then it's not very fair. All right, let's keep going. Okay, so we are with this guy named Matt. Matt has 3 pairs of dark socks and 6 pairs of white socks. Okay, let's write that down. So dark socks. The probability of dark socks, it looks like he has 9 total socks, so we are going to say 3 out of 9. Okay, and we can simplify that to 1/3. We also have white socks, okay, and it says that he has 6 pairs of white socks. So this is going to be 6 out of 9, or this is going to be 2/3. Okay, so hang in there with me. If the socks are dark, Matt will choose an outfit that includes dress pants. So if these socks are dark, then he will always wear dress pants. So the probability of dress pants, if he selects dark socks, is always going to be a probability of 1. Okay, so we would say the probability equals 1 here for dress pants if he selects dark socks. Okay, so that's right there. So Matt will choose an outfit that includes dress pants. So dark socks given dress pants. Okay, if the socks are white, Matt will toss a coin. If he gets heads, he will wear jeans. If he gets tails, he will wear shorts. So with the white socks, we have 2 options here. We have jeans and we have shorts. And this is based on a coin flip. So what are the probabilities of wearing jeans? Well, you guys should know that's 1/2. And the probability of wearing shorts is also 1/2. Okay. And I'm gonna try and make this like a little tree diagram here. So dark socks goes to dress pants, whereas white socks can either go to jeans or to shorts. Okay. Now let's answer some of these questions here. What is the probability that Matt will wear white socks to school? Well, we already know that he has 3 out of 9 for dark and 6 out of 9 for white socks. So that's going to be 6 out of 9, or if you're fancy, simplify it to 2/3. What is the probability that Matt will wear shorts to school? So the probability of shorts, well, remember, wearing shorts is dependent on whether or not he picks some white socks. So the white socks probability is going to play a huge role here. So what I'm going to do is I'm going to take the probability of the white socks, okay? And then, so after that first event, right, then I have the second event of flipping the coin. So I'm going to put a square around that, flipping the coin. And the probability of wearing shorts is 1/2, okay? Now, to combine these two probabilities, I'm not going to add them. I am going to multiply them together. So the probability of Matt wearing shorts to school is going to be 2 out of 6. So that is the probability of Matt wearing shorts to school. If you used, if instead of 2/3 you use 6/9, you would get the same answer, 6/9, right, times 1/2, which equals 6/18, which you can divide the top and the bottom by 3, right, to get 2/6. We can simplify this further to 1/3, but you guys get the point. So the probability of wearing shorts to school is 2 out of 6. What is the probability that Matt will wear dress pants to school? So remember that dress pants, dress pants, the probability of dress pants relies on whether or not he wears dark socks, okay? So the probability of dress pants is equal to, we need to take the probability of dark socks, so that's going to be, I'm going to use the simplified version of 1/3. You can use 3/9 or you can use 1/3. And then we're going to multiply that by the probability of dress pants. Well, we said the probability of dress pants, if he chooses dark socks, is 1. So what's 1/3 times 1? It is 1/3. All right, what is the probability that Matt will wear jeans with dark socks? Well, as you guys know, if he picks dark socks, he's going to wear dress pants. So the chances of that happening is 0. Is Matt equally likely to wear dress pants, shorts, or jeans today? Explain your answer. So let's take a look at our probabilities here. Right, so dark socks and dress pants, we said we did 1/3 times 1, which equals 1/3. So this is dress pants. I'm going to change colors here. Purple is going to be shorts. We said the probability of shorts is 2/3 times 1/2, and that was 2/6, or it simplifies to 1/3. Hey, look at that. Check mark there. Okay, last one we got to check is jeans. Jeans, remember, relies on white socks, so we're going to take 2/3, right, the probability of that, times the probability of jeans. We get 2/6. Hey, that is 1/3. So yes, he has an equally likely chance of wearing dress pants, shorts, and jeans. Yes, equally likely. Awesome. Cool. Let's keep going. So Ryan is experimenting for her class. The pronouns are a little off here, guys. I will be consistent and change it to he, because I think he is used the rest of this. So Ryan is experimenting for, for his class. I can speak English. He has a bag containing 1 green marble, 1 blue marble, 1 red marble, and 2 yellow marbles. He also uses a coin with heads on one side and tails on the other. Ryan conducts 12 trials, randomly pulling out only 1 marble and doing 1 coin flip at a time. Here are the results of his experiment. So this right here is super important, because when they ask you for the experimental probability, which they do below, your denominator is going to be 12. Please do not make it 24. All right, let's take a look. So we want to do, we want to find the experimental probability that he draws a yellow marble and tails. I know I'm skipping A right now. I'm going to come back to it, I promise. Okay. So what is the experimental probability that he draws a yellow marble and tails? So I need to look at my data here. And then on my table, I need to find the results YT. So I'm going to look at this. Hey, look, there's a YT. There's another YT. So it looks like I have 2. Well, 2 out of how many? 2 out of 12. That is my experimental probability. If you simplify, that's okay. I will take either answer. So 2/12 or 1/6, or if you'd like to make that a percentage, I believe that's about 17%. Okay? There we go. Now we're going to figure out what the theoretical probability is. So remember, we can use either a tree diagram or we can use an area model. So I'm going to go through both. So the first thing is the marble, right? That's our first event. And the different options for marble, we have one green marble. We have a green. We have a blue marble. We have a red marble. And we have 2 yellow marbles. Okay, so we just list all of our possible outcomes. The second event is the coin, right? And remember, for each color marble that we pick, they are going to have either heads or tails. So we are going to list like this: heads or tails, heads, tails, heads, tails, heads, tails, and heads, tails. So when we write our outcomes, we're gonna list all of them. So for my green marble, I can either have green and heads or green and tails. For my blue marble, I can have blue and heads, and then I have blue and tails. For my red marble, red and heads. I think you guys are getting the picture here. Yellow marble, yellow heads, yellow tails, and then we have it twice. So there is my tree diagram, or some version of it. I also want to do an area model really quick. Okay. So I have my square. My left side is going to be my marble. And then my top side is going to be my coin toss, right? So again, I need to think about how many different options I have for marbles. So I count 1, 2, 3, 4, and 5. So I'm going to split my square horizontally into 5 equal sections. So 1, 2, 3, 4, and 5. There we go. More or less 5 equal sections. And I'm going to label the colors here. So there's a section for green, blue, red, yellow, and yellow. Okay, now I need to split my square vertically, and I only have 2 options for my coin, so I'm going to split it down the middle. Boom, there we go. So, and then I'm going to label heads, tails. So again, I come out with the same outcomes: BHBT, RHRT, YH, YT, and another YH and YT. Okay, so either way works. You will get the same answer. So we need to ask ourselves, well, what's our denominator for the theoretical probabilities? Well, let's count how many outcomes. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks like it's going to be out of 10. Let's double check with the area model. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Excellent. Cool, so they're the same. So what do they want us to do? Yellow marble and tails. So I'm going to look at all of my outcomes. How many times do I get yellow and tails? Boom, boom, right there. So that's going to be 2 out of 10, or that is going to be 1 out of 5. Or if you want to change it into a percentage, right, that's going to be 20%. All right. How would you explain the differences you found between the experimental and theoretical probabilities? So in this case, I would say there isn't too much of a difference because, 20% isn't that far from 17%. But I want you to tell me, how would you explain the difference? Why are they different? Well, remember that there are, or I would say there's room for error in experiments. There's room for error in experiments. Another thing you could say is something along the lines of I forgot what I was going to say. I lost my train of thought. There isn't too much of a difference. There's room for error in experiments. There we go, I remember it. If we conduct more experiments, the experimental probability and theoretical probability will get closer together. Okay. So again, you could include any of these parts, but I want you to explain the differences. A lot of you on the quiz just told me the difference between theoretical and experimental probabilities. That's not what the question was asking. It's asking you to look at your values for each type of probability and then explain why are they different. Okay? All right, here we're going to get into some area models here. Okay? So Leon uses squares to make a board. He randomly throws a stone onto the board. What is the probability the stone lands on a space marked 3? So we're trying to find the probability of 3. Well, how in the world are we going to do this? Well, I would, whenever you're doing a question like this, I would try and find your denominator first. Okay? So we need to split this square into nice even pieces. So if you notice, we have 4 even little squares there, so which actually we could split these larger squares into. So why don't we just go ahead and do that? Okay? Boom, there we go. So how many total squares do I have? How many small squares do I have? I have 1, 2, 3, 4. This is by 1, 2, 3, 4. This is a 4 by 4 square. So it looks like I'm going to have 16 small squares. Now, let me erase some of these dots here. I want to figure out the probability. Oops, I can't see this. So just imagine this is perfect. I can't see the 3 here. And that's a 2. Okay, so we don't need that. Awesome. So we need to figure out the probability of landing on a space marked 3. So let's count them. There's 1, there's 2, there's 3, there's 4, and then how many squares are here? Well, there's another 4, so I would say this is 5, 6, 7, and 8. So there are 8 squares out of a total of 16 marked with the space 3. So the probability of hitting a 3 is 1/2 or 50%. Or if you like 8 out of 16, that works too. Okay, so there we go. So split your area model into smaller equal pieces, and then you can find your probability that way. All right, let's keep going. Number 5, a gumball machine contains orange, yellow, and purple gumballs. The probability of getting an orange gumball is 3/4. So probability of orange, I'm going to write these down just so I know, is 3/4. And then probability of yellow is 1/6. 2/1/6. What is the probability of getting a purple gumball? Explain how you determined your answer. So remember, the sum of all the possible outcomes of an event or of any situation should equal 1. So the sum of all probabilities should equal 1. This is something that's very important. Should equal 1. Oops. Should equal 1. Remember this, okay? So we have orange, yellow, we're missing purple. So we need to add 3/4, right? Probability of orange plus the probability of yellow plus the probability of purple, and that should equal 1, right? So what I would do is I would add these two probabilities together. So let's see, let's find a common denominator, I think, of 12, right? So I'm going to multiply 3/4 by 3/3, so I get 9/12. Then I can multiply 1/6 by 2's, and then I get 2/12. So it looks like I have 11 out of 12, which is orange and purple, or orange and yellow, excuse me. So how many does that leave for purple? Well, if I do 12 out of 12, which is 1, and I subtract 11 out of 12, because remember, this 11 out of 12 is orange and yellow, that leaves us 1/12 for purple. So the probability of purple is 1 out of 12. And there we go. Okay. If there are 36 total gumballs in the machine, how many are purple, how many are yellow, how many are orange? So remember, for orange, there are 3/4 of our gumballs are orange. So if there are 36 total, what is 3/4 of 36? We're going to multiply 3/4 times 36. So I see some cross-canceling capabilities. So 4 goes into 36 9 times, and then 4 goes into 4 once. So it looks like I'm going to have 27 orange gumballs. We're going to do the same thing for yellow. Ooh, there we go. For yellow, my probability is 1/6. 1/6 of 36. Well, I see some cross-canceling capabilities again. 6 goes into 36 6 times. 6 goes into 6 once. Multiply straight across, so I'm left with 6/1, which is the same as 6. So I have 6 yellow gumballs. Lastly, we need purple. Purple, the probability of purple we said is 1/12. So out of 36, right, again, cross-canceling, 12 goes into 36 3 times, 12 goes into 12 once, and I'm left with 3/1, which is the same as 3, so I have 3 purple. Let's add these together. Do they equal 36? 27 plus 6 is 33, plus 3 is 36 total. Excellent. There we go. There are my gumballs. Okay. Let's keep going. Oh no, that was it. Never mind. Look at that. I lost track of time. Excellent. All right, guys. I hope this helped. I wish you the best of luck on your test. Remember to go slow. Double check your answers. Okay? All right. Happy studying, and I will see you on test day.